All right, in this video, we are going to continue with more examples of evaluating limits of one of these three indeterminate types. So, with example 8, we want to consider this limit here. So it's the limit as x tends to 0 from the right of x plus e to the x raised to the power 1 over 3x. So let's check to see what type this is. Maybe it's not indeterminate at all. So let's look. Well, what happens? As x tends to 0 from the right, our base is tending to 0 plus e to the 0. That's 1. So the base is tending to 1. And what about that exponent? 1 over 3x. Well, if x is very close to 0 and bigger than 0, 3x is a very small positive number. 1 over 3x is going to be very large and positive. So this exponent 1 over 3x is tending to infinity. This is of type 1 to the infinity. That is indeterminate, could take lots of different values. Let's see what the value of this limit is. Well, we're going to apply the approach outlined in the last video. What was that? Well, we're going to let y, first of all, equal the function we're interested in. So that's x plus e to the x to the exponent 1 over 3x. And now we're going to take the limit, not of y first, but the limit as x tends to 0 from the right of the log of y. When we do that, when we take the log of y, it's the log of this, which has this exponent. The exponent 1 over 3x is going to pop down in front of the log, and we'll get that this is equal to the limit as x tends to 0 from the right of 1 over 3x times the log of x plus e to the x. And now what do we have? Well, this looks like it would be most natural, given that we're multiplying by this fraction, 1 over 3x, if we were to write this as the quotient, the limit as x tends to 0 from the right, of the log of x plus e to the x, all over 3x. And let's look at what this limit looks like. Okay, well, x gets close to 0 from the right. Log x plus e to the x tends to log of 0 plus e to the 0. That is the log of 1. And the log of 1, you'll remember, is 0. So the numerator here is tending to 0. And the denominator, as x tends to 0 from the right, tends to, well, 3 times 0 is 0 as well. So this is an indeterminate form, and this is the type of indeterminate form to which L'Hopital's rule applies. And I don't think that we would be able to evaluate this limit using a more elementary method. In other words, I think using L'Hopital's rule here is essential. So what do? Well, remember, we're going to just evaluate the derivative of the numerator and the derivative of the denominator. And what are we going to get? We'll have, this is equal to, limit as x tends to 0 from the right, differentiating that numerator, we're going to get 1 over x plus e to the x using the chain rule. Derivative of the inner function is now 1 plus e to the x, so we get that in the numerator. And differentiating that denominator, 3x, we just get 3. As always, after differentiating, we'll just do some simplifying before considering this limit again. So this looks like 1 plus e to the x all over 3 times x plus e to the x. And now, what can we say about this limit? Well, maybe this isn't indeterminate at all. It won't be as long as the denominator here is not tending to 0. In other words, as long as 0 is in the domain of this function. And 0 is in the domain of the function. If you evaluate this denominator at 0, you're going to get 3 times 0 plus e to the 0. That's just 1. 1 times 3 is equal to 3. So 0 is in the domain of this function. The function's continuous, so what do we get for our limit? Our denominator is, as we said, going to be 3, and the numerator is tending to 1 plus e to the 0, which is 1 plus 1, which is equal to 2. Okay, so now we've found the limit as x tends to 0 from the right of log y. Well, we wanted the limit as x tends to 0 from the right of x plus e to the x to the exponent 1 over 3x. In other words, we wanted the limit as x tends to 0 from the right of y. And we know the limit as x tends to 0 from the right of log y. From this, we can finish up. We say, so the limit as x tends to 0 from the right of x plus e to the x to the exponent 1 over 3x. That's the limit we were first interested in. That's the limit as x tends to 0 from the right of what we called y. We write y in terms of the log of y. We write it as e to the log y. We do that because we know that as x tends to 0 from the right, log y tends to 2/3, and so e to the log y is going to tend to e to the 2/3. So this equals e to the 2/3, and that's our answer. Our next example is the limit as x tends to infinity of x to the exponent 1 over x. So what type is that? Well, the x as x tends to infinity, of course, tends to infinity. And the exponent 1 over x, well, for very large values of x, 1 over x is going to be very small and positive, so that exponent is tending to 0. So this is of type infinity to the 0. That's indeterminate. I'm going to let you do this one as an exercise. So you try to do this one yourself. For our next example, we're going to try to evaluate the limit as x tends to 0 from the right of x to the sine x. So what type is this? Well, as x tends to 0 from the right, this base here is tending to 0, and the exponent is tending to sine 0, and sine 0 is 0. So this is of type 0 to the 0. That's, again, an indeterminate form. So how are we going to do this? Well, we're going to use exactly the method that we've used for the last few examples. So what do? We're going to, again, let y equal x to the sine x, and then we're going to try to take the limit as x tends to 0 from the right of log y. When we take the log, that exponent, sine x, can be brought down in front of the log. So we have this limit here. Now, what type is this? Well, as x tends to 0, from the right, that sine x is tending to sine 0, which is 0. So this is of type 0 times, and as we've seen before, as x tends to 0 from the right, what can we say about y equal to log x? X tends to 0 from the right, log x tends to minus infinity, so this is of type 0 times minus infinity. All right, how do we evaluate limits of type 0 times minus infinity? Well, remember, we're going to take one of the two factors and put it in the denominator as its reciprocal. And you can try either one, but I'm going to try putting sine x in the denominator as its reciprocal, as we did a couple of videos ago. All right, now what does this look like? Well, the numerator, that log x, is still tending to minus infinity, and for x very close to 0 and x bigger than 0, sine x is going to be close to 0 and bigger than 0. So we're going to have 1 divided by a very small positive number, which is going to be a very large positive number. So that denominator is tending to plus infinity. So this looks like type minus infinity over infinity. All right, so this is the sort of limit to which L'Hopital's rule applies. So it's the limit as x tends to 0 from the right. And what can we do? Well, maybe I should just say, if you like, at this point, you could recognize that 1 over sine x is cosecant x and differentiate that way. If I do that, I'm probably afterwards going to change that derivative, minus cosecant x cotan x, back into a function in terms of sine x and cos x to recognize the limit. So I'm just going to leave it as is, as 1 over sine x, and we'll differentiate this using the quotient rule. So what do I do to apply L'Hopital's rule? I differentiate the numerator, and I differentiate the denominator separately. So the derivative of log x is 1 over x. So 1 over x here. And now, differentiating this 1 over sine x using the quotient rule, derivative of 1 is 0. And then minus, we'll have 1 times the derivative of sine x. So we'll have minus cos x in the numerator and the denominator all squared, so sine squared x. All right, now what do we do? Well, after applying L'Hopital's rule, after differentiating, your function might look a bit messy. So, as always, we try to rewrite this a bit. And what does this look like? Well, this now looks like minus sine squared x over x cosine of x. Okay? Well, now that we've simplified this, can we evaluate the limit? Well, if 0 actually is in the domain of the function, we'd be good. But in fact, if you evaluate that denominator at 0, the limiting value, you'll get 0. So the denominator is tending to 0, and the numerator is tending to sine 0 squared, which is also 0. So once again, we have a limit of type 0 over 0. All right, well, this is the sort of limit to which L'Hopital's rule applies. So this is now the limit as x tends to 0 from the right of differentiating sine squared x using the chain rule. We have 2 sine x times the derivative of sine x, which is cos x, divided by differentiating that denominator, x cos x, using the product rule. Derivative of x is 1. Leaving the second, we have cos x, and then plus, leaving that x, and then differentiating cos x. Derivative of cos x is minus sine x. All right, so now let's look at our new function that we obtained after applying L'Hopital's rule. Is 0 in the domain of this function. It will be in the domain of the function as long as the denominator is not 0. And when x is 0, the denominator isn't 0 because the denominator is going to be cosine 0, which is 1, plus, evaluating this bit here, you get 0. So the denominator is going to equal 1 plus 0, which is 1. So it's not 0. And evaluating the numerator, we have minus 2 sine 0. Sine 0 is 0. times cos 0. 0 times 1 is just 0. All right, so this is 0 over 1, which is equal to 0. Good. We have found the limit as x tends to 0 from the right of log y. But remember, what we wanted was the limit as x tends to 0 from the right of x to the sine x, which is to say we wanted the limit as x tends to 0 from the right of what we called y. All right, so remember, we weren't done yet. What is y in terms of log y? Well, that's e to the log y. And what is this? Well, as x tends to 0 from the right, we found that log y tended to 0. So e to the log y tends to e to the 0, which is 1. All right, so that's our limit. All right, with our next example, we are supposed to evaluate the limit as x tends to minus infinity of e to the x over x minus 2. So this is a limit of a quotient, and we might wonder, can we apply L'Hopital's rule, or do we need to? Certainly, this might not even be an indeterminate form. We should always be thinking about that. So what is happening to this numerator? First of all, as x tends to minus infinity, what happens to e to the x? Well, when looking at a limit involving e to the x or log x or some other function that we know well, it's always a good idea to draw the graph of the function. So here I've drawn y equals e to the x, and we're asking, what does e to the x look like for large negative values of x? Well, for large negative values of x, which are out here, e to the x we can see is positive, but very, very close to 0. And so as x tends to minus infinity, e to the x actually tends to 0. So this numerator here is tending to 0, but what about the denominator? Well, for large negative values of x, x minus 2 is, well, a large negative value of x. We subtract 2, you get an even larger negative value of x. So that denominator is actually tending to minus infinity. All right, so in particular, whether or not you thought this was an indeterminate form or not, you certainly couldn't evaluate this using L'Hopital's rule in its current form. Remember, you can only use L'Hopital's rule for indeterminate forms of type 0 over 0 and infinity over infinity, and you really should only use L'Hopital's rule when other more elementary methods, such as the ones that we used in Intro Calc Part 1, cannot be used. All right, now looking at this, is this actually indeterminate at all? Could a limit of this type take multiple values? Well, the answer is no. If you have a limit and the numerator is tending to 0 and the denominator is tending to minus infinity, the limit is always going to be 0. In this particular case, think about it. If x is large and negative, this e to the x is going to be a very, very small positive value, and the denominator is going to be a very, very large negative value. If I take something very, very close to 0 and divide it by a really large negative value, I'm going to end up with a number that's even closer to 0. This limit here is equal to 0. And that's all there is to that. For our last example in this section, we're supposed to evaluate the limit as x tends to 1 from the right of e to the 1 minus x, all raised to the exponent 1 over 2x minus 1. And we could, if we wanted to, use our rules of exponents to rewrite this, but it's not even necessary. First thing that we should do is check to see what type of limit is this, and is it even indeterminate? Do we need to resort to sophisticated methods? Well, what happens here? As x tends to 1 from the right, this 1 minus x is tending to 1 minus 1, which is to say 0. What is e to the 0? E to the 0 is equal to 1. So this base here is tending to 1. What about the exponent that we have here, 1 over 2x minus 1? Well, as x tends to 1 from the right, or the left for that matter, 1 over 2x minus 1 tends to 1 over 2 times 1 minus 1, which is 1 over 2 minus 1, which is just 1 over 1. Actually, the exponent is just tending to 1. So this isn't actually a indeterminate form. It's not, for example, a limit of type 1 to the infinity or anything like that, or it's not a type, let's say, infinity to the 0 or 0 to the 0. It's nothing like that at all. It's not indeterminate. What is the value? There's only one value that this limit could possibly take. If you give me an x that's close to 1, our base is close to 1, the exponent is close to 1. If I take this number close to 1, raise it to a power that's close to 1, I'm just going to get 1 to the exponent 1, which is equal to 1. That's all we have to do. This limit is equal to 1. All right, that's it. So lesson here again is only use L'Hopital's rule for indeterminate forms of type 0 over 0 or infinity over infinity, or for one of our other types of indeterminate forms, and then you apply the L'Hopital's rule after turning the limit into a limit of one of these two types.